Hey there, welcome to the lecture for section 6.4, Solving Trig Equations. All right, let's start with some simple equations. Say I want to solve for t here. The sine of t equals 1/2, and I'm interested in values of t that are between 0 and 2 pi. All right, so recall that the input to a trig function is an angle, so I'm looking for the angle whose sine is 1/2. Right? Well, if I look over here at the unit circle, okay, where do I find a sine of 1/2? Sine is the y-coordinate of the terminal point of an angle. So I see there's one there, okay? So one solution here is going to be pi over 6 radians. Are there any others, right? Are there any other angles between 0 and 2 pi where the y-coordinate of the terminal point is 1/2? Well, it looks like there is another one right here at 5 pi over 6. So we see that there are two solutions to this equation, the sine of t equals 1/2, where t would be between 0 and 2 pi, or once around the unit circle. All right, look at the next one here. Sine of theta is equal to square root 3 over 2. Now this one says for all possible values of theta. Wow, all possible values of theta. What does that mean? Well, it means in the first quadrant if there's one, or second, third, fourth, and we could just keep going round and round the unit circle. Well, let's begin by finding the first solution. All right, the sine, again, we're looking at the y-coordinate of the terminal point. Where is a sine square root 3 over 2 on the unit circle? Well, the first occurrence that we see it at is right here. There's a y of square root 3 over 2. And that's at pi over 3. So that's one solution. Do we see it anywhere else as we go around the unit circle? Well, we do. We see it again right here at 2 pi over 3. So there's two solutions. Oops, 2 pi over 3, not 2 pi over 2. There's two solutions. Are there any others? Well, no. There's not going to be any other y-coordinates or square root 3 over 2 or 2. But since we want all possible values of theta, or all possible angles, right? Well, there's one that terminates at pi over 3. There's another that terminates at 2 pi over 3. But what if I just keep going around the unit circle? If I make a whole trip around and then come back again, right? There's pi over 3 plus 2 pi, right? Here's 2 pi over 3 plus 2 pi. What if I go backwards around the unit circle? I could say pi over 3 and go all the way around again minus 2 pi. So one way of specifying all possible values would say that the angle could be pi over 3 plus or minus 2 pi k, or 2k pi, however you want to say that, where k is any value, any value. And then we could also say it's 2 pi over 3 plus or minus 2 pi k. All right. All right. Let's look at another example. This one wants us to find all the solutions to the sine of theta equals 0.65. So we want to find all again. We want to find all the values, all the angles that have a sine of 0.65. Well, let's look at a diagram, all right? Or let's draw ourselves a unit circle. All right, if the sine of the angle is 0.65, that's the y-coordinate of the terminal point is 0.65. So I think, I don't know, maybe there's a nice estimate of where that angle might be. There's theta right there. And the coordinates on that terminal point will have some x-coordinate, don't care what it is, but the y-coordinate is going to be 0.65, right? So there's one occurrence. There's another one, right? There's another one that's going to happen over here. The x-coordinate is going to be whatever that value is, but the negative of it, but it's going to have the same y-coordinate, 0.65, right? So I have two angles in one trip around the unit circle. How do I know what those angles are going to be, though, right? So call it theta sub 1 and maybe theta sub 2, right, for the two angles. Theta sub 1 and theta sub 2. Well, I can use my calculator to find one of them, right, by taking the inverse sine of both sides, right? So if I say the inverse sine of the sine of theta is equal to the inverse sine of 0.65, right? The inverse sine will undo the sine, and I'll see that first occurrence of theta, call it theta sub 1, it's going to be the inverse sine of 0.65. Let's see what that is. I can get my calculator to wake up. There we go. Inverse sine, 1 second, sine of 0.65. There it is. I'm in degree mode. Do we want to be in degree mode? I see pi, and I don't see any degree symbols, so no. I don't. I'm going to switch back to radian mode for this. Generally, we want to use radian mode unless we see a degree symbol. Okay, unless we see a degree symbol. All right, so let's try that again. I'll just do second entry, enter for entry to repeat it. Now we're in radian mode, and there's our answer, 0.7076 radians. All right, so that's theta sub 1. Now, what about the second one? Well, theta sub 1 here, the second one has the same reference angle. The reference angle is actually equal to theta sub 1, right? So theta sub 2 could be pi minus theta sub 1, right? Or pi minus 0.7076. Let's see what that is. Pi, there it is, minus 0.7076, 2.4399. We'll say 2.434. Let me put a 0 there just to be consistent with 4 decimals. So there's 2, but we want all, right? Since we want all, we're going to have to add the plus 2 pi k, or plus or minus 2 pi k. Or plus. It doesn't, we don't have to say plus or minus. We really could just say plus. I'll just do it both ways. It's supposed to be a 2. All right. Okay, one more. Here we want to find all solutions to the cosine of x equals -4/5. Oh, but we're going to just stay on one interval here. We're just going to stay in once around the unit circle. 0 is less than or equal to x is less than 2 pi. All right, so where would 4/5 be on there? Let's sketch our unit circle and see. Oh, -4/5. Okay, the cosine is negative left of the vertical axis over here, right? So -4/5 is maybe right there. Okay, so let's see, the cosine would be -4/5. I don't care what y is. Right? Is there another place that has another angle? So there's one angle. Call him, let's see, we're doing x now, so we'll call him x sub 1. There is another one though, right? It's going to be right here. The x coordinate of that terminal point is still -4/5. Y is whatever it was up there, but negative. All right, so there's a second angle now. It's all the way around here. We'll call him x sub 2. Can there be a third or a fourth? Nah. Now I could use my calculator for this, but you know, would it be? Yeah, the calculator would be fine. I could also make a triangle. I think we'll just use the calculator. Right? So we know that the cosine of x is -4/5. Take the inverse cosine of both sides. So x then is going to be the inverse cosine of -4/5. Let's see what that is. Inverse cosine -4 divided by 5, 2.4981. All right, so that's, what angle do we just find? X sub 1 or X sub 2? Well, we've just found X sub 1, right? Because the domain is restricted to quadrants 1 and 2 for the inverse cosine. All right, so how do we find what that X sub 2 is? That second angle. Well, let's see. It looks like, okay, so if this angle here is X sub 1, it looks like this angle here is the same, just negative X sub 1, right? So that means that X sub 2 could be considered 2 pi minus X sub 1, right? Or 2 pi minus that 2.4981. All right, let's see what that is. 2 pi minus, I'll just say answer so I don't lose anything in the rounding. So second negative sign, that's 2 pi minus the previous answer. All right, 3.7851. These are all, of course, approximate, but that's okay. We can approximate them when we're doing this. All right. All right, let's look at this example here. This in cosine of x equals 0.71. We want the smallest 3 positive solutions. All right. Always, always, always start with your diagram. Make a unit circle just to see where these angles are going to fall. Right. The cosine is 0.71. Right. Cosine, that's the x coordinate of the terminal point. Right. So where is? Let me draw a better one. Where is x going to be 0.71? We know x is 1 over here. 0.71 is maybe about right there. So, you know, I don't know. Maybe it's right there. That might be our x, our first angle of x, and you might call it x sub 1. All right, our cosine is positive 0.71. Y is something we know. There's another cosine where? That's positive 0.71. Down here in quadrant 4, right? There's only this one in the restricted. All right, so we're going to go down here in quadrant 4. That's where we get another cosine of 0.71. The y is whatever it is, but the negative of what it was up there. All right. So we've got an x sub 1, and then look, we want the 3 smallest positive solutions. So that means I got to start here and go all the way around to here, and that guy will be my second angle. But it wants 3, right? Well, there's 2, 1, 2. Is there anywhere else on the unit circle that the cosine is 0.71? No. So that means I'm going to have to just want positive solutions. We don't want negative, so we just go around this unit circle in the positive direction all the way till we get to another, and there it is, another cosine of 0.71. So this whole big angle here, that guy is going to be our x sub 3. All right. What are they? Well, find x sub 1 first, because that's the angle that's in the restricted domain for the inverse function. Take the inverse function of both sides, so then x is going to be equal to the inverse cosine of 0.71. Let's find out what is our x sub 1. Let's see. Inverse cosine 0.71, 0.7813 radians. All right, there's that first angle. What's that second angle? Now, can I express it in terms of the first angle? Yeah, look, it looks like x sub 1, positive x sub 1 is this guy here. So negative x sub 1 is this guy here, which happens to also be equal to x sub 2. So I could say x sub 2 is 2 pi minus x sub 1. Or 2 pi minus 0.7813. All right, let's see what that is. 2 pi minus 0.7813, 5.51, or I'm sorry, 5.5019. And here's our x sub 2, but we need x sub 3 also. Let's see what that one is. X sub 3, so that's the whole thing around, so that's 2 pi, and then plus x sub 1. So 2 pi plus x sub 1, or 2 pi plus 0.7813. So that's going to be 2 pi. Let's put that in the calculator. 0.7813. And we see it's 7.0645. All right, so there's our 3 smallest positive solutions to this equation. Okay, let's look at another one. Well, this one looks a little bit more interesting. We're still going to do the smallest 3 positive, the 3 smallest positive, whatever. Okay, we're still doing that. But this equation is a little bit interesting. Look, I have to manipulate this a little bit. And look at the argument. The argument to the trig function is an expression, right? With solving trig equations, if we were wanting to write steps to solve trig equations, the first thing that we always want to do is isolate the trig function. All right, so let's see. I need to get the cosine 4x by itself. That means I'm going to need to divide both sides by 3. So then I can say that the cosine of 4x is equal to 2/3. All right, well, that's a starting point. But look, when I'm dealing with arguments to trig functions, those are angles, right? But I'm not solving for the angle here. I'm solving for x, right? So the next thing I want to do here is I want to make what we like to call a u substitution. We want to substitute u for the expression that is the argument. All right, so we'll say let u equal 4x. Let's rewrite that with u now. Now I can go ahead and I can solve. Cosine of u is 2/3. Now I can go ahead and I can solve for the 3 smallest positive solutions for u. All right, so we'll go ahead and solve for u. All right, and in the process, what the process of solving for u is, first, just like we've been doing, right? I want to use the inverse function for the first angle. But we know there's going to be more. We're looking for 3, right? So I use the inverse function for the first angle. Let's go ahead and do that. All right, so the inverse of both sides. So cosine -1 of cosine of u is equal to inverse cosine of 2/3. All right, so what is u going to be then? U, the first one anyway, call it u sub 1, is going to be the inverse cosine of 2/3. Let's see what that is. It's 0.8411. All right, there's one solution for u, all right? So we got the first angle by using the inverse function. Now we need to sketch the unit circle to see what our remaining, where our remaining angles are going to go, all right? So sketch unit circle, whoops, for remaining angles. All right, so here's your unit circle. Let's try that again. Okay. All right, u is 0.8411, so there's the first. Let's see, u, that's the cosine. So 0.8411 has the cosine of 2/3. So where is that going to be? That's going to be, I want to say, we're just going to estimate it right there. There's our u sub 1. All right. It has a cosine of 2/3 and some y. All right, where do we have another positive cosine? We have it in quadrant 1. We also have it in quadrant 4. All right, so we have another one down here where the cosine is 2/3 and the y is the negative of whatever it was up there. All right, so there's our u sub 2, our second angle. So how do I express that? Well, that's going to be what? Looks to me like 2 pi minus u sub 1, right, is the best way of expressing u sub 2, which of course is 2 pi minus 0.8411. And we'll just leave it like that. We want to find the 3 smallest positive, though, so we need another one. Well, let's see if we start here through positive. So we're going to start here and go in the positive direction. We'll go all the way around, and the next angle is going to be this one right here. All right, this will be our u sub 3. A good place for it. Let's put it maybe over here. There's our u sub 3. This big angle. Looks like that's 2 pi plus u sub 1. Or 2 pi plus 0.8411. All right, so I've got 3 solutions for u, okay? And then now I've got to back substitute, though, because I didn't want u, I wanted x. So the next thing we're going to do is undo that u substitution. All right, let's do with u1 first, right? So 0.8411 has to equal, u is equal to 4x, right? Equals 4x. So x then is going to be 0.8411 divided by 4, right? So what is that one? There it is. Divided by 4, 0.2103, right? So there's our x sub 1. Oh, what did I say? 0.21 what? 0.2103. All right, so there's x sub 1. X sub 2, well, that's just going to be the 2 pi minus 0.8411 divided by 4, right? Which is, let's find that, 2 pi minus 0.8411, enter, and then divided by 4, 1.3605. There's our x sub 2. And there's one more, right, x sub 3. That'll be the 2 pi plus 0.8411 divided by 4. So that's, oops, not this guy. So that's plus 0.8411. Enter, then we'll divide that by 4. That's going to be 1.7811. Okay? So there's our three smallest positive solutions for x. Woo! This takes a minute, doesn't it? Let's do another one. Look at this guy. Here we want to solve 3 times the sine pi over 4x equals 2 for the 3 smallest positive solutions. We're doing that again, all right? 3 smallest 3 positive solutions. All right, what was that first step again? That first step was isolate the trig function. I'm not writing these again. Isolate the trig function, right? So we'll need to divide both sides by 3. So now we have the sine of pi over 4x is equal to 2/3. Okay, now let's do a u substitution. We'll let u be that pi over 4x. So then the sine of u is going to equal 2/3. All right, let's use our inverse trig function to find the first angle, right? So inverse sine of both sides. So u then is going to be the inverse sine of 2/3, which is inverse sine 2 divided by 3, 0.7297 when we use 4 decimals. All right, so let's draw that. Let's see where we're at on the unit circle. Okay, if the sine is 0.7297, that's the y coordinate of the terminal. No, the sine is 2/3. Okay, so the positive y of 2/3, that's going to be about here, I would say. So there's our first angle. There's our u1, our u sub 1. Okay, and that's 0.7297. The sine, I don't know what x is, but the sine is 0.7297. There we go. No, 2/3. I keep getting those reversed. Okay, the sine here is 2/3. Where else is the sine 2/3? Well, the y's are positive, quadrants 1 and 2. So we have another angle over here. That's the negative of whatever that x coordinate is, but the y coordinate is the same. It's 2/3, right? So we know our u1, it's 0.7297. Our u2 is this guy, our second u, okay? And the reference angle for that u sub 2 is u sub 1, right? This guy equals this guy. So I can then say, well, he's u sub 1. Let me write that better. We can then say our second angle is pi minus u sub 1, right? Or pi minus 0.7297. What's the third going to be? We're only going in the positive direction, right? Start at the beginning, go all the way around again, stop here. There's our u sub 3. Our u sub 3 then is going to be pi plus u sub 1, or pi plus 0.7297. All right, we found our 3 angles for that sine function. Now we need to undo this u substitution, right, for x sub 1. So we'll say 0.7297 equals pi over 4x. All right, well, let's multiply both sides by 4 over pi, right? So to undo it, right? So here, let me show you. With a little space. Pi over 4x. If I multiply both sides by 4 over pi, then I'm left with just x on the right. Okay. These will all divide out. So my x sub 1 then is 4 times 0.7297 over pi. And let's see what that is. 4 times, I can keep all my decimals, I can just say answer. Come back. 4 times answer. Okay. Hit enter. It's that divided by pi. And it's 0.9291. So there's x sub 1. It's one of our answers. Now we need x sub 2. X sub 2, that's going to be 4 times, what was u sub 2? Pi minus 0.7297 over pi. Let's see what that is. All right, so we'll do it this way. We'll say pi minus 0.7297 is that, times 4 is that, divided by pi is 3.0709. radians. All right, so there's x sub 2. I did that right. I think I did. All right, and now we need x sub 3. One more, right? Kind of out of room. I'll put it in. I'm going to go way up here to find x sub 3. So I ran out of room. X sub 3 then is 4 times pi plus 0.7297 over pi. All right, we'll do it this way. Pi plus 0.7297. So that times 4 equals that divided by pi. 4.9291. Okay. So there's our three answers. 0.9291, 3.0709, and 4.9291. Okay. Let's end with one more example here. Let's come back to that Ferris wheel application. Remember that guy from 6.1? All right, we got a couple. It's a little bit different here, not a whole lot. We've got a Ferris wheel. It might be misspelled. That's okay. We're going to let it stay misspelled. I'm not very good at spelling. A Ferris wheel with a radius of 67.5 meters. Okay, it's centered 69.5 meters above the ground. Okay, all right, so here's our Ferris wheel. Okay, its radius is 67.5 meters. Okay, so there we go, 67.5 meters. The center is 69.5 meters above the ground. That's the center. So that means the ground must be another 2 meters below that. So this must be 2 meters right here. Okay. So we've got radius of 67.5. We've got one there. We've got the other radius up here. What's our diameter? 135. Right. So that's what's going on. It completes one revolution every 30 minutes. Okay, if it goes around every 30 minutes, that's going to be our period, isn't it? All right, how long is this rider? 100 meters above the ground. All right, well, we want to determine how long it's 100 meters over the ground, we're going to need to find the height function, right? We're going to need to find the height function. So the graph of that, if we graph height as a function of time on the vertical axis and time on the horizontal axis, right? Okay, we can see that when we start out, we're 2 meters above the ground. The time is 0, right? When we're all done, we're back where we started from. So what is it, 30 minutes later, we're back down here. At the height, at the very peak, we're at the top of the Ferris wheel, we're 67 times 2, or what is that, 135 plus 2, we're at 137 feet, all right? So that's going to be about there. Okay, 137. That's at the high point. We hit the high point halfway between when we start and when we're done. So that's about 15 seconds. There's our high point. Okay, so we're starting down here. We're going up high. We hit the highest point, and then we're going to come down back low again, and we end here. That's one revolution of that Ferris wheel. Okay. Well, to write the formula for h of t, the height as a function of time, I need to, it's cyclical, it's periodic in nature, right? So it's going to be a periodic function. It's going to be sinusoidal, because that looks like a sinusoidal graph, right? If it does another revolution, it'll just repeat itself again and again and again. So we need to decide, do we want to do a sine or a cosine here? Well, I think this looks very much like a reflected cosine curve. Recall that the cosine curve with no transformations looks like this. And the sine curve with no transformations looks like this. Oops, I did too much. Let's try it again. One period of the sine curve with no transformations, one period of the cosine curve. So this looks like a reflection of the cosine curve. So I think that that's what I want to write. The standard form for the cosine function, right? Call it h of t. It's going to be the amplitude times the cosine times b, right, which correlates to the horizontal stretch or compression, times t, bt. Now, do we have, I don't think we have to deal with a horizontal shift here, because look, I started right on the vertical axis. So I can make this a little easier, not deal with a horizontal shift, but I do have a vertical, don't I? So plus k. All right, let's see if we can write that function. Okay, so where's our midline here? It's halfway between the low and the high. So the midline is, we'll say right there, halfway between 137 and 162, or at the center of that circle. So that's going to be 69.5 right there. Okay, we know our period is 30. I think we can pretty much find everything we need. If we know the period is 30, from the period we can find the horizontal stretch or compression, b, right? Because recall, if the period is 2 pi over b, then we can say that b is 2 pi over the period, and the period, of course, is 30. So b then, they'll simplify to pi over 15. We have everything we know to write that equation now. The equation h of t is going to equal the amplitude. Okay, amplitude is halfway between the high point and the low point, or the radius of the circle. So that's going to be 67.5, but we've got a reflected cosine curve, so it's going to have to be negative. Okay, negative 67.5 times the cosine of, we found b was pi over 15 times t. And then what is our midline? 69.5, so plus 69.5. Okay, well there's our formula, there's our equation, if you will. Now, what do we need to answer with that equation? How long is this rider 100 meters above the ground? All right, where's 100 meters? Somewhere in between here. We're going to say it's here. Okay, so I need to find these two times. One is here and one is here, right? We got a t sub 1 and a t sub 2. That's the distance, but the length of time between these two times is going to tell us how long that rider is 100 meters above the ground. All right. So how do we go about finding this? Well, we know that height is 100, so we're going to solve the equation. 100 equals, oops, 100, and my little tablet likes to go crazy sometimes. 100 equals all of that. Now let's see, where I wrote so big, I don't have a lot of space left. So you know what I think I'm going to do? I'm going to come over here and erase our Ferris wheel. And we're going to solve that equation over here. Okay, so 100 equals negative 67.5 times the cosine of pi over 15 t plus 69.5. Okay, first step is we need to isolate that trig function. So let's subtract the 69.5 from both sides. Okay, so then 30.5, is that what that is? No. 30.5 is going to equal negative 67.5 times the cosine of pi over 15t. All right, it's isolated. We got to divide both sides by that negative 67.5 now. All right, so negative 30.5 over 67.5 is going to equal the cosine of pi over 15t. Okay, we're going to need to make a u substitution here. All right. So we'll let u equal the pi over 15t. All right, and we're going to rewrite this with u, and then we'll solve for u. So negative 30.5 over 67.5 equals the cosine of u. All right, let's take the inverse cosine of both sides. So our first u then, our u sub 1, is going to be the inverse cosine of that negative 30.5 over 67.5. And let's see what that is. Oops, wake up. Inverse cosine negative 30.5 divided by 67.5. Value is 2.0396 radians. There's u sub 1. We need u sub 2 though, right? Let's make a unit circle. And let's see if we can figure that out. Probably going to lose this. Let's erase the graph. We're going to need, well, it's not. Let's put the little unit circle right up there. All right. So we have a negative cosine. So we're over here in quadrant 2 and eventually in 3, but the first one will be in 2. That's 2.036 radians. We'll say that one is about right there. All right. So we have that negative cosine of negative 30.5 over 67.5 and some y. There's another one down here, right? So here's our u1. That's the 2.3039. Did I copy that number down? Yeah, no, that's right. 2.0396 radians. Now u sub 2 looks like it's going to be 2 pi, because look, that angle there matches this angle here, which is the same as u2. So it looks like my second, so this is my first occurrence. Now my second occurrence is over here at 2 pi minus u sub 1, or 2 pi minus 2.0396. Let's see what that is. $2.0396. Okay, it's 4.2436. Okay. Yeah, that's right. Okay, so now what? Let's see. We've got our two u values. We've got to undo the u substitution. All right, we have to undo the u substitution. So u1 is 15, or pi over 15t, right? So t then is going to be the 2.0396 times 15 over pi, right? Here, let's put that over here. 2.0396 is equal to pi over 15t. To solve for t, we're going to multiply by 15 over pi, both sides, of course. Okay, so they'll all divide out. So our first t then is 15 times 2.0396, which is that divided by pi. .7384. All right, that's the first time, 9.7384 seconds. Very accurate, aren't we? Now let's find the second one. Our second time is 4.2436 times 15 over pi. That's our second time. Let's see what that is. Okay, 15 times 4.2436 is that, divided by pi. .2617. Okay, so this T1 is 9. T1 is 9.7384 seconds. T2 is 20.261, oh, not seconds, minutes, 2617 minutes. How long was it above, or was the rider above 100 feet? So how long are we on this part of the curve? Well, that's going to be 20.2617 minus 9.7384, which is 7384, 10.5233 seconds. Probably more accurate when we then, or minutes, sorry, 5233 minutes. I keep wanting that to be seconds, but it's minutes. Wow. So there we have it. The rider was above 100 feet, about 10.5 minutes. All right, this ends the lecture for section 6.4, trig equations.